In this lecture, I will discuss about the reducibility of a representation, and the content of this lecture is from the textbook of Mathematical Methods for Physics and Engineering by Riley, Hobson and Benz. Now, in our earlier lectures, we have already seen that it is possible to have more than one representation of any particular group. For example, if you consider the group 1i minus 1 and minus I, that is comprising these 4 elements, under ordinary multiplication, and it has been shown to have a set of 2 by 2 matrices and a set of 4 unit matrices In as two of its possible representations. These two representations we have already discussed in our earlier lecture. Now consider two or more representations d1, d2 in this way up to dn, which may be of different dimensions of a group G. As we have obtained two representation for this particular group, so similarly we are considering a group G, and suppose we have obtained different representations such as d1, d2 in this way up to dn. Now combine the matrices d1x comma d2x in this way up to dnx that correspond to element x of G. If you consider a particular element x of G and suppose you have obtained different representation corresponding to the element x, so these representations are d1x, d2x, dnx, etc. And how you are combining? So you just look at this block diagonal matrix D. D is known as the block diagonal matrix, and these diagonals are actually different representations. So d1x, d2x, which are the different representations corresponding to the element x, we are writing them in the diagonal, and all other elements are 0. So capital D is a block diagonal matrix. Then D, capital D, which we can say that is the set of matrix Dx, is the matrix representation. So what is D? D is the matrix representation of the group obtained by combining the basis vectors of d1, d2 in this way up to dn into one larger basis vector. So what we have done actually, we have combined the basis vectors of d1, d2 in this way up to dn into one larger basis vector. That we have done actually. If knowingly or unknowingly we had started with this larger basis vector and found the matrices of the representation D to have the form shown in equation 29.9. That is, we know that to find a representation we need the basis vectors, and suppose if we had started with this particular basis vector, we had started with this larger basis vector and found the matrices of the representation D to have the same form. So in that case the representation would have same form as described by this equation, or to have a form that can be transformed into this by a similarity transformation. We have already discussed about the similarity transformation. Then we would say that D, that is this matrix D, is reducible, and each matrix Dx can be written as the direct sum of the smaller representation. That is Dx that can be written as the direct sum of the smaller matrices such as d1x plus d2x. This plus symbol is used to denote as the direct sum, and direct sum of the smaller matrices. So dx is equal to d1x plus d2x in this way up to dnx. It may be that some or all the matrices d1x comma d2x themselves can be further reduced. That is, they can be written in a block diagonal form. So let us discuss this issue. For example, suppose that the representation D1. Suppose we are considering the first representation, that is D1, and say we have a basis vector x, y, z transpose, that is coordinates. Then for the symmetry group of an equilateral triangle, whilst x and y are mixed together for at least one of the operations x, suppose if you consider rotation operation, then we have already discussed this fact that in this operation x and y are mixed together, but z is never changed, small z is never changed. In this case, the 3 by 3 representative matrix D1x can itself be written in block diagonal form as a 2 by 2 matrix and a 1 into 1 matrix. So let us check that is how the block diagonal matrix dx can now be written. So dx is equal to, now you see that this is a 2 by 2 matrix ABCD, and this indicates that x and y are mixed together, and this is a 1 by 1 matrix, and this indicates that z is unchanged. So overall D1 matrix, these D1 matrix can be further reduced, and they have been written as a direct sum of 2 by 2 matrix and a 1 by 1 matrix, and all other rest of the matrices are unchanged. So now the structure of dx will look like this one, 29.10. When all the other representation D2x have been similarly treated, suppose just like D1, we can also consider, that is whether D2, D3 they can be further reduced or not. So after reducing all the representations, if possible, then what remains is said to be irreducible and has the characteristic of being block diagonal, that is they have a block diagonal form with blocks that individually cannot be reduced further, that is we cannot reduce them further, because we have already checked that whether they can be reduced or not, and we have expressed D in block diagonal form, and now the blocks cannot be reduced further. The blocks are known as the irreducible representations of G. So now the blocks will be known as the irreducible representations of G, often abbreviated to the irreps. We call it irreps of G, and we denote them by d cap I, and in that case the blocks will be denoted as d cap I. Any representation can be written as a linear combination of irreps. So any representation can be written as a linear combination of the irreps. Now suppose if any particular representation D each constitute irreps di may appear any number of times. So suppose in a particular representations D, each constitute representation d cap I that may appear many number of times or not at all, subject to the restriction that the sum of all the irreps dimensions must add up to the dimension of D itself. So this is very important, that is the sum of all the irrep dimension must add up to the dimension of D itself. Now let us say that d cap I appears mi times. So that appears mi number of times. The general expansion of D is then written as D is equal to m1 into d cap 1 plus m2 into d cap 2 plus in this way up to mn into d cap n. So this representation D, they can be expressed in this summation form. So where in generally we are saying that is d cap I appears mi number of times. For example, d cap 1 appears m1 times, d cap 2 appears m2 times, in this way. So D can be written in this summation form, where all these are d cap I are irreducible representations. Now we can draw some conclusion concerning the block diagonal matrix. Those components of the basis vector that correspond to rows in the representation matrices with a single entry block, that is a 1 by 1 block, are unchanged by the operations of the group. This fact we have already discussed. For example, where we have shown that is the D1 matrix can be separated into a 2 by 2 matrix and a 1 by 1 matrix. So that 1 by 1 matrix actually correspond to Z. In the example which we given earlier, that the entry on the third row forms a 1 by 1 block, implies that the third entry is in the basis vector xyz transpose, namely Z, is invariant under the two-dimensional symmetry operation on an equilateral triangle in the xy plane. So suppose if the entry is expressed in a 1 by 1 block form, then we have to be sure that the Z component is invariant. Similarly, the largest sized block located on the row or column corresponding to a particular coordinate in the basis vector is n by n. Then the coordinate is mixed by the symmetry operations with n minus 1 others and is said to transform according to an n-dimensional E-depth of G. This fact we have already discussed. That is, in the matrix, suppose x is the first entry in the complete basis vector. If you consider the basis vector, so here x is the first entry, and the first row of the matrix contains two non-zero entries. You see the structure again. So in this first row contains two non-zero elements. First column also contains two non-zero elements. So x is part of a two-component basis vector whose components are mixed by the symmetry operations of G. The other component is y. So actually here x is mixed with the y, and this fact we have already discussed in our some earlier lectures also. Now we will give some examples regarding the E-depths of G. So we return again to the group G of two-dimensional rotation and reflection symmetries of an equilateral triangle, or equivalently the permutation group S3. This may be shown using the methods given below to have three E-depths. So they have total 3 E-depths. So how we are saying that is they have total 3 E-depths. Firstly, we have already seen that the set M of 6 orthogonal 2 by 2 matrices given in our earlier lecture is isomorphic to G. We have discussed the fact that is, suppose if G is the symmetry elements of an equilateral triangle. In our earlier lecture we have considered 6 orthogonal 2 by 2 matrices which are isomorphic to the group G. So what are the matrices? This set of 6 matrices which we have already discussed. These 2 by 2 orthogonal matrices are isomorphic to the group G. These matrices therefore form not only a representation of G but a faithful one. That means each matrix they have a one-to-one correspondence to each of the elements for the symmetry group of the triangle. That is why these matrices form a faithful representation. It should be noticed that although G contains 6 elements, the matrices are only 2 by 2. However, they contain no invariant 1 by 1 subblock. That is, we have already discussed about the significance of the 1 by 1 subblock. Significance of the 1 by 1 subblock means that is a particular representation they can be separated into representation. That is a first by a 2 by 2 matrix and another is a 1 by 1 matrix, and that 1 by 1 matrix that signifies that sum of the basis vector is unchanged for a particular application of symmetry. So in this case the matrices are only 2 by 2 and they contain no invariant 1 by 1 subblock, which for 2 by 2 matrices would require them all to be diagonal, and neither can all the matrices be made block diagonal by the same similarity transformation. They therefore form a two-dimensional irreducible representation of G, as they cannot be reduced further. So these 6 orthogonal matrices actually form two-dimensional irreducible representation of the group G. And secondly, every group has one unfaithful irreducible representation in which every element is represented by the 1 by 1 matrix I1, or more simply by 1. That is, if we represent every element as a 1 by 1 matrix, that is by 1, then this particular representation is also a irreducible representation, but we have to say that this is unfaithful, as all the elements are 1. That is why we are saying that is this representation is unfaithful. And thirdly, there is another unfaithful irreducible representation of G, and is given by assignment of the one-dimensional set of 6 matrices. So this set of 6 matrices is again 1 by 1 matrices, but all are not 1, just like the previous case, and the first 3 are 1 and the next 3 are -1, and these particular elements correspond to the symmetry operation I, then 2 rotation operation, and then 3 reflection operation respectively. So IR R prime corresponds to 1 1 1, and the 3 reflection operation corresponds to -1 -1 and -1, and these elements corresponds to the in general group elements. If we generalize them, they are IAB and CDE. So IAB corresponds to 1 and CDE corresponds to -1 respectively. In terms of the permutation group S3, we have already discussed the permutation group. Permutation group is also isomorphic to the group G, and in terms of the permutation group, the positive and minus negative sign can be defined. So 1 corresponds to even permutation and -1 to odd permutation. So what is odd permutation and even permutation? Odd or even referring to the number of simple pair interchanges to which a permutation is equivalent. Suppose if you interchange a pair, so number of pair needed so that the permutation is a equivalent one, that is the permutation is unchanged. So that number will indicate whether it is a odd number or even number, and depending upon the odd number or even number, there will be the sign. That is, for odd it will be 1 corresponds to even permutation and -1 corresponds to odd permutation. So how to write down the all 3 irreducible representation of G? So we are writing this in this particular table. In the first row we are writing the elements. So the elements in generalized form is I, A, B and C, D, E, and there are total 3 irreducible representation. The first one is that all are 1 and we are denoting as A1. So in the left side column, they are the irreducible representations or irreps. And next one is the A2. We are denoting them as A2. So for A2, 3 elements will be 1 and another 3 will be -1. And the next irreducible representation will be the 6 set of orthogonal matrices, and we are denoting that particular representation as E. So E is the set of 6 orthogonal matrices, and we are writing them as MI, MA, MB, MC, MD and ME. So these are the respective matrices. So in this way, for the symmetry group of equilateral triangle, there are 3 irreducible representation, and we have already discussed that is what do you mean by reducible representation and irreducible representation. So we have obtained 3 different types of irreducible representations, and they are written in this particular format of the table. So these are all about reducible and irreducible representation, and I hope you have understood the content of the lecture. And for further understanding, I request you to go through the textbook of Riley, Hobson and Benz, and I thank you all for listening this lecture.